Hello and welcome. In today's video, Convergence, we are going to explore an essential topic in probability theory, the different modes of convergence. Understanding these modes of convergence is crucial, not only in mathematics, but also in field like finance, where they are applied to model asset price, risks, and more. We will go over four types of convergence. Convergence in probabilities, almost sure convergence, convergence in distribution, and convergence in LP. Each of these modes has its unique application and significance, especially when analyzing the behavior of financial data. By the end of this video, you will understand how they relate to practical problems, include finance. So let's dive in. Let's begin with an overview. There are several different ways in which sequence of random variables can convert. Depending on the application, you might need a different type of convergence. In this video, we will cover first, convergence in probabilities. How likely is it for random variables to approach a target? Or mutual convergence, what happens to the random variable in almost all cases, and convergence in distribution, how the distribution of random variables changes over time. And last, convergence in LP or mean convergence, how the expected values or power of the difference behave. Each of these play an important role in probability theory, and as we will see later, they are widely used in financial models. First, let's talk about convergence in probability. A sequence of random variables Ln converts in probability to a random variable x if for any small epsilon greater than 0. The probability that xn and x are further apart than epsilon goes to 0 as n increases. We can write as limit here. As n increases, the probability that the distance between xn and x is larger than epsilon becomes smaller and smaller. In finance, this can this can be useful when analyzing how the price of a stock might stabilize, allow a fair value or expected price over time. For financial example, let's consider an example from finance. Imagine you are modeling the price of stock using a stochastic process. As time goes on, you expect the price to converge to a certain long-term value. Convergence in probability allows you to assess how likely the stock price is to deviate from the expected value as the time progresses. Next, we have almost sure convergence, which is a stronger form of convergence. Here, a sequence xn converges almost surely to x for almost every comeout. The sequence xn will eventually get arbitrary arbitrary close to x and stay close forever. We can right here. Almost sure convergence guarantees that for most possible outcomes, the sequence behaves as expected. This form of convergence is particularly important when you need to ensure that the sequence converges for almost all possible scenarios. Now, let's discuss convergence in distribution, also known as weak convergence. A sequence of random variable xn converge in distribution to x if as n approach to infinity, the distribution functions of xn approach the distribution of function x. Uh, Formally, we can write as here. And this form of convergence is about the overall shape of the distribution rather than the value of the random variable themselves. The distribution of xn become increasingly similar to the distribution of x as n increases. Convergence in distribution is widely used in finance when applying the central limit theorem. For instance, when modeling returns of a portfolio, even if the individual asset returns are not normally distributed, the overall portfolio returns may converge in distribution to a normal distribution as the number of assets increase. And next, we have convergence in LP, which is often called mean convergence. Here, the expected p power of the distance between xn and x trend to zero. In special case, where p equal to 2, this is known as mean square convergence. Convergence in LP means that the expected difference between xn and x shrink to zero as n infinite. This is useful when you care about how the average deviation behave. And now let's summarize the relationship between these different modes of convergence. There is a hierarchy. First, almost sure convergence implies uh, convergence in probability. And next, convergence in probability imply to convergence in distribution. And convergence in LP imply to convergence in probability. However, the reverse implications do not hold. For example, convergence in distribution does not imply convergence in probabilities. This hierarchy is particularly relevant in financial risk management. Depending on the level of certainty you need, you might choose one mode of convergence over another. For example, convergence in distribution might be enough for pricing your load, while convergence in probability could be more useful for modeling risk. Let's walk through an example of convergence in probability. Consider the sequence of random variable xn equal to 1 over n as n equal to infinity. Xn converges to 0. And for any epsilon greater than 0, we can see that uh, property of uh, norm xn minus 0 greater than or equal to epsilon equal to 0 for large n. Yeah. This, this shows that the probability of xn being far from 0 becomes smaller and smaller as n increases, which is exactly what convergence in probability describes. Now, to wrap up things that we talked today, we have discussed four key modes of convergence: convergence in probabilities, or mutual convergence, convergence in distribution, and convergence in LP. Each mode has its own strengths and application. In finance, these modes of convergence are crucial when modeling asset price, risk, and distribution of return. Thanks for watching video, and if you found this video helpful, don't forget to like, share, and subscribe for more content on mathematical finance. See you next video.